In this practical example, we're going to use the theory of hierarchical design to implement a 4-bit full adder, as well as demonstrate how hierarchy is achieved in Verilog and Quartus. As we saw in the previous screencast, hierarchical design concerns the use of modules and submodules to develop a full system as a sum of interconnected parts. In this example, our full system is the 4-bit full adder, which we'll design as a module consisting of 4 1-bit adder submodules. Why would we want to design our system like this? Wouldn't it be easier to just create a single module for the 4-bit adder? Well, by creating a 1-bit adder module, we could implement it any number of times to create an n-bit adder as necessary. As we learnt in the last screencast, hierarchical design is all about reusability, and a single-bit full adder module is a very useful component to have in digital designs. As we're starting a new design, we first need to lay out the specifications for what we need. Looking at the hierarchy diagram, we know that we need a 4-bit adder module instantiating 4 1-bit adder submodules. We want to be working from the bottom up here, so we'll first spec out the 1-bit adders. Taking the gate level RTL as a reference, we can see that we need 3 inputs, 2 single-bit ports, A and B, and a carry-in port. For our outputs, we've just got 2 single-bit ports, sum and carry out. The module needs to implement the circuit shown here, which can be represented by these 2 Boolean expressions. As for the 4-bit adder specification, we know that we'll have 2 4-bit input ports, and again a carry-in line, and a 4-bit sum output port, and a single-bit carry-out port. This module doesn't need describing as a Boolean expression, as it will get far too complicated, so we can just say that it implements 4 1-bit full adders. Now that we've specified our design, it's time to start building it. First off, you're going to need to create a new project, so if you haven't done that already, pause the video now and do it. Remember everything I said in the last lab session about keeping projects separated. You'll be creating a modified version of this project later on, so I suggest using a parent folder to hold all of this week's tasks and saving this one in there. We're going to start with the 1-bit adder module, so create a new Verilog file and immediately save it as 1-bit fulladder.v. Notice that I'm following the naming convention of using camel case starting with a capital for module names. First things first, we're going to include a header to show some metadata about our module. I've got one on my clipboard already, so you don't have to watch me type it out line by line. So our header needs to contain information about its creator, the date of creation, and an explanation of what each port is for. We're doing this as a brief form of documentation. For more complex IP, you'd need a full user manual to be able to use it. It's just handy to have a port list here. So we can now start to build our module. I tend to start with an empty interface and implementation just so I can get the layout sorted, and so that I remember to include the end module statement. We then declare the ports in the interface. The order in which you declare the ports is not strictly defined by good practice. For small designs like this, it makes sense to keep the inputs and outputs together, but once you get onto more complex designs, it may be a better idea to group them by the submodules that they relate to. With the interface declared, we can start to implement our design. First off, we need to declare any internal wires that we might need. Looking at the RTL, we can see that we'll need 3 wires to connect the gates together, so we'll give them some names and then declare them in the module. We can then use either the RTL diagram or the Boolean expression to determine our Verilog statements for the 2 outputs. Starting with sum, we need inputs A and B connected to an XOR gate, with the output connected to our wire 1. And wire 1 then needs to be connected to another XOR gate, along with the carry-in signal to produce our output. We can then run analysis and elaboration to check the resultant circuit in the RTL viewer. So analysis and elaboration has not been successful. Let's have a look why. According to the debugger, top-level design entity 4-bit full adder is undefined, which has caused the compiler to stop and that stage of compilation to fail. From what we've learnt about hierarchical design, we know that the top-level design entity is the module at the top of the system's hierarchy. So when we've only got one module in our system, it should be at the top. When you compile a project in Quartus, it needs to know what the top-level design entity is, so that it knows in what order it needs to compile the design into a circuit. When you create a new project, Quartus assumes that the top-level design file has the same name as the project, so it's looking for a file called 4-bit fulladder.v. Now, as we haven't designed it yet, there's nothing for it to find, and so compilation has stopped. We can rectify this by setting our 1-bit adder module to be the top-level design entity, and we can do this using the project navigator. In the drop-down box, we can choose the Hierarchy tab to view the hierarchy of our system. We can see here that it currently thinks a module called 4-bit full adder is at the top, indicated by the symbol next to it. By navigating back to the Files tab, we can right-click on our 1-bit adder file and select Set as Top-Level Entity. Now, when we go back to the Hierarchy tab, we can see that Quartus now knows to treat the 1-bit full adder module as the top level of our design. So let's run analysis and elaboration again. Once that's completed successfully, we can look at the RTL viewer to see our circuit. We can see here that Quartus has done some optimization and shows the 3 inputs A, B and C in as connected to a single XOR gate with the output being passed to sum. For the moment, the carryout is undefined and therefore unconnected, so let's go back and finish off the design. So to generate the carryout signal, we need to AND the output of the first XOR gate with carry in, and the 2 input values, and OR the results of those expressions. Let's run analysis and elaboration again and see what we get. Looking in the RTL viewer, we can see that we've got the circuit that we wanted. For this session, we'll just do a visual check compared to the RTL diagram to verify it. We'll be simulating it properly in the next lab session. The RTL presented in the viewer is rearranged, but all connections are correct and we can assume that the module will work as expected. Now we need to push on and create our 4-bit adder module. So we'll create a new file and immediately save it as 4-bit fulladder.v. While it's still fresh in our minds, we'll use the project navigator to set this new file as the top-level entity. We can see from the Hierarchy tab that this has been successful. We'll add in our header. As they're very similar, we can just copy and paste the one from our single-bit module and just modify the module and port descriptions to fit our needs. As before, we construct the module's outline and declare the ports. Note that I'm using the same identifiers here as I have done in the single-bit adder module. This is perfectly okay practice, as there is no danger of redefining the scope of a variable in Verilog hierarchy, unlike in sequential programming languages where you have to deal with local and global variables within a single file. So now we can start instantiating our submodules. We'll call the module's name, and declare the name of our instance, and then use the instance's interface to wire it up to our parent module. So looking at the interface for the 1-bit adder module, our first port is input A, which we want to connect to bit 0 of our A bus. Next is input B, which is connected to B0, and as this is the first instance, which will make up the least significant bit of our adder, our carry-in signal is connected to the carry-in of the parent module. For the outputs, sum is obviously connected to bit 0 of the parent module output, but what about carry out? It needs to be connected to the next instance of the 1-bit adder, and so we need to use a wire. We know from our diagram that this isn't the only wire we'll have to use. We'll need links between the first 3 full adders in our design, so instead of declaring separate wires, we can just use a 3-bit bus. Each wire can then be referenced as a single net in that bus, and everything is kept nice and neat. So we'll declare the wire in our code and finish off connecting our instance, closing off the interface with a bracket and semicolon. We then repeat this process for the second instance, this time connecting the carry-in signal to the carry-out of the previous. Note that I've renamed this instance to adder2. Each instance within a module must have a unique name so the compiler knows which is which. Repeat this process 2 more times, and in the final instance, make sure you connect the carry-out to the output of our parent module. Now that that's done, we can perform a full compilation and take a look at our final design. So my compilation failed this time. I put semicolons instead of commas in the module's interface. Hopefully you spotted this when following along. If not, make the same change and try again. Now that our design has compiled, we can take a good look at it. First thing to notice is that our 4-bit full adder module has now taken its place as the top-level design entity in the hierarchy window. We can click the drop-down box next to it to show the submodules that it instantiates, as well as the names of those instances. If we open the RTL viewer, we've got a similar story. As opposed to the gate-level RTL that was shown in the last lab session, the RTL viewer displays our 4-bit adder module at a higher level of abstraction, showing the instances of the 1-bit modules as well as their ports. We can use the plus symbols to take the lid off this black box representation and get a better look at what's inside. You can understand why the RTL viewer works like this. With even such a simple design as the one we have now, opening up all instances creates quite a large circuit that's difficult to follow. If you were working with a really complex IP here, it wouldn't make sense at all, so it's good to be able to look at things from a higher level of abstraction. I suggest that you also take a look at the technology map and the chip planner to further build on what we were talking about in the last lab session and see how this design is physically implemented on the device.